Welcome back. In this video, we're going to be discussing fatigue strength. That is, how do we come up with a number that corresponds to how much stress we think we can put a part under to last a certain amount of cycles. So recall, in the last video, we talked about the approach to evaluating fatigue analysis is really determining the number of cycles or the life that a product or a component will last. So we determined fatigue strength experimentally in a very similar way that we determined static strength. So recall, with static strength, we developed a test where we put a part under some tensile load and we clock how much the strain changes with respect to that stress. So if we take a part like steel, we see this typical diagram where we have the linear part which obeys Hooke's law. It comes to some point, which we called our yield strength, where it starts to plastically deform, and then finally it breaks at some ultimate strength. Oftentimes the ultimate strength can be much higher than the yield strength. So we put the machine in a test specimen, usually looked like a notched test specimen, and we pull on it and get these numbers. Now we use the tensile test to come up with our yield strength and our ultimate strength in tension. And we can do some assumptions, assuming that compression or bending stress likely gets us the same results. And it turns out those assumptions are just fine. In fatigue analysis, it turns out that how we load the thing actually matters. And because there's basically an infinite way of loading things, there's no way that we can come up with an absolute prediction for whether or not something's going to fail. So in practice, when engineers develop a fatigue test stand, what they'll do is they'll take their actual part and put it through the fatigue test rather than trusting these generic properties. But let's go ahead and figure out how we come up with these generic properties. So fatigue strength and the numbers we'll use for fatigue strength come experimentally from what's called an R.R. Moore test. And this test stand basically takes a part, again it will be some notched component, and puts it under pure bending, an absolute bending moment, and then rotates that part n number of cycles. And depending when this thing breaks is how we define our test specimen. So some important things about how you prepare this test, because it will affect our values later, is that it is a polished test specimen. It is under pure bending. That is, no axial load, no torsion. And we compare all our values to this. So most of fatigue analysis is doing what's necessary to account for the fact that, in general, our parts are not polished test specimens. They're usually not in pure bending. And our situation will have its own uniqueness. So what this test actually looks like, and you can YouTube a few videos, is there's some test specimen which rotates and it records the number of cycles until failure. So this is a good example of a fatigue test on a particular carbon steel, and at some point it quickly fractures. So that's a great example of fatigue failure, of that quick, brittle fracture. So what you do when you do a fatigue test is you do those types of tests over and over and over again at different values of bending moments in order to figure out how many cycles it will last. And what you come up with is a nice diagram. So I'm going to be developing our fatigue strength diagram. This fatigue strength diagram will aid us as we are looking at different aspects of our fatigue analysis. So for this diagram, we'll put the stress S that we put our component under, and on a log scale, we will do n the number of cycles. So a cycle is that load being fully reversed. So a particular point on the shaft is in at its maximum and it's in tension, and then it rotates around and it's in its minimum value, which is in compression, and then it's going to rotate around again and get back to the maximum. That's one cycle. So if we put it under a certain amount of stress and it broke the very first time, then we could say, well, if it breaks at the very first loading, then that ought to be the ultimate strength. And that's what we see. So if n equals 1 here, or will basically be 0, at not being able to complete one cycle, the loading must be the ultimate strength. We can also look at 10 to the third cycles, 10 to the sixth cycles, 10 to the seventh, and so on. The number of cycles is in a log scale. All right. If we bring the stress value back down a little bit, perhaps it will last a few more cycles. And the amount of time it lasts generally is longer and longer the lower we decrease that stress value. So in this portion of the region, from 0 cycles to about 10 to the third cycles, we call this low cycle fatigue. So at whatever point it breaks, we can plot that. And so obviously this is a line fit, and statistically we'd have points all around here. But we'll line fit it for between the low cycle fatigue. So our equations work okay for low cycle fatigue that we'll be using, but by and large, fracture mechanics will give you a much better estimate of how many cycles something can take if we're talking about it lasting less than 1,000 cycles. Between 10 to the third and 10 to the sixth, we also see the same sort of behavior, slightly different slope to this line. And again, our experiment values may be sort of around this. But this is what's called high cycle fatigue. So anything between 1,000 cycles to 1,000,000 cycles. And this period, everything below 10 to the 6 cycles, we're going to call finite life. On average, for typically, we say anything more than 1,000,000 cycles is called infinite life. And now it's not called infinite life because really it will last forever. What we mean is that likely the part will not have any failure. All right, so after 10 to the 6 cycles, if our stress is low enough, we find that for many materials, this slope tends to level out. So if we did some experimental values, they'd be all over the place. If we line fit, there's this knee. This is called the knee of the graph at 10 to the 6 cycles, which forms. So steel has a strong knee. Aluminum does not have as much of a knee. But for our consideration, at about 10 to the 6 cycles, or 1,000,000 cycles, the part begins to have an infinite life. So if we put this part under stress at some value here, we expect that the part will not break indefinitely, or till we basically want to be able to replace the part. So this line here is the fatigue strength, or the endurance strength. So the fatigue strength is a value with respect to n. So at low cycle fatigue, we have a higher fatigue strength. And if we're talking about infinite life, if we want an infinite life, we're going to have a lower fatigue strength. But there is some value here that's important to us, and that is what type of stress do we need to keep this part under such that it will last more than 1,000,000 cycles. This is the hypothetical endurance limit. So our fatigue strength, as I just said above, is a fatigue strength with respect to the number of cycles. Our endurance limit is a value of stress the fatigue strength at 10 to the 6 cycles for steel is our hypothetical endurance limit. That is, at this stress value, it will last at least 10 to the 6 cycles. We do not have a good way to say how many cycles it will last. We can only say it'll basically last 1,000,000 cycles, which should be good enough. If it's going to last less than 1,000,000 cycles and more than 1,000 cycles, what we're going to do is we're going to put a line fit between the endurance limit at 10 to the 6 cycles and our ultimate strength, come up with a line fit and estimate the number of cycles that we think it can last if it's going to last less than 1,000,000. So our process in doing endurance or fatigue stress analysis is the part going to last 1,000,000 cycles? And if not, we're going to find out how many cycles it can last. So how do we know these endurance strengths? Well, this is a material property, or it's the ideal endurance limit is a material property. And for the most part in this class, we're going to look at two metals. We're going to look at aluminum, and we're going to look at steel. So steel has a endurance strength of about half, a hypothetical endurance strength, generally of about half the ultimate strength, except for very high strength steels. So the endurance strength, or the hypothetical endurance strength, under this pure bending situation is equal to about 0.504. For most part, we can just use half the endurance strength, multiplied times the ultimate strength, as long as our ultimate strength is less than about 200 kpsi. That's equivalent to about 1,400 megapascals. Otherwise, we basically set it as a limit. So it limits out at about 107 kpsi, which is equivalent to about 740 megapascals. So that is if the ultimate strength is greater than about 1,400, well, let's keep the same system, 200 kpsi or 1,400 megapascals. For aluminum, the endurance strength is about 40% of the ultimate strength, or this hypothetical one based on pure bending. So 0.4 times our ultimate strength, or about 19 kpsi, which is equivalent to about 131 megapascals. As long as, so we have the same sort of limit, as long as the ultimate strength is less than or equal to about 48 kpsi, which is 328 megapascals. This is rounding up. If your strength is larger than that, again, we just sort of set a limit on it. So in order to find the ultimate strength, we just need to look in the tables in the back of the book and then multiply either by 50, multiply by either 50% or 40%. So that gets us our hypothetical endurance strength.